So let's have a little bit of a go. Function is given by find the stationary points and state their nature. So stationary points, right pen, implies f dash of x is equal to 0. So let's work out, so therefore 9x squared minus 4 is equal to 0. So 9x squared is equal to 4. X squared equals 4 on 9. X is equal to plus or minus 2/3 if we take a square root. So that means my stationary points are at positive 2/3 and something, negative 2/3 and something. So if I substitute 2/3 into my function, 3 times 2/3 cubed minus 4 times 2/3 plus 1. So 2/3 cubed, if I cube the top and cube the bottom, I get 3 times 8 on 27 minus 4 times 2 is 8 on 3 plus 1. Make them all on 27. I get 24 on 27 minus 72 on 27 plus 27 on 27. So 24 plus 27 is 51, gives me negative 21 on 27. So what I'm hoping now for negative 2/3, I can just go through and change some signs. That's going to be a negative value there. I get 4 times negative 2/3 is positive. So I'm going to make that one positive and 1 stays positive. So in this case, I'm going to get for f of negative 2/3 equal to negative 24 plus 72 plus 27 over 27, which is 75 on 27. Okay, so state their nature. So if I want to state their nature, by right, I should do a little sign diagram. So what I do is, even if I just mark out, let's call these little points here, negative 2/3, and positive 2/3, okay? So all I look to do is try and work out the nature of the derivative either side of negative 2/3. So for example, I've got 2/3 here, negative 2/3. If I pick negative 1, say, and I work out f dashed of negative 1, what do I get? I get 9x squared, which is just 9 minus 4. So I get a positive answer. So I get a positive slope. I then get a 0 slope at negative 2/3. And if I just say pick 0, and I put 0 into the derivative, f dashed of 0, f dashed of 0 is negative 4, it's negative. So at negative 2/3, I get a maximum. Okay, so then if I now extend that 0, if I put positive 2/3 here, I know the gradient is 0. And let's pick positive 1, which is on the other side. If I put positive 1 into that equation, I get 9 minus 4, which is a positive gradient. So you can see I get that, which makes it a minimum. So I've got their nature. So at 2, that's a minimum at x equal to 2/3 and a maximum at x equal to negative 2/3. So if I plot those points, 2/3 negative 21 on 27, which is, we'll say, a little bit smaller than 1. And the other point is, oops, my bad. That should be at negative 2/3, 75 on 27. So that's close, a bit under 3. So what if we rub out a little bit of scribble there and just mark it a point at negative 2/3, nearly 3. So something like that. 5 on 27. And obviously the other point then at positive 2/3 is going to be at negative 21 on 27, which is a little bit under 1, which might be about there. If I put x equal to 0, I get y equal to 1, which we can call that point there. So it's a cubic graph. So I've got a graph that comes up, it turns there. I know it goes through there, and then it turns, and then it comes back up again. Now I'm not going to find the x-intercepts. X-intercepts, we put y equal to 0. So if I solve 3x cubed minus 4x plus 1 equal to 0, I might have to do a division, I might use my CAS. We can get those values there, okay? Let's put 2/3 negative 21 on 27. All right, what about 2x cubed plus 1? I should know roughly what that looks like. Find the stationary points and state their nature. So f dash of x is equal to 6x squared. So stationary points occur at x equal to 0. At f dash of x equal to 0. So if I solve 6x squared is equal to 0, that implies x is equal to 0. So if I check the gradient, like that, if we do it that way, if I put x equal to 0 there, and then I'll have negative 1, positive 1, just the value either side. So f dash of x is 0 at x equal to 0. If I put negative 1 into the derivative, I get positive 6, so it's a positive gradient. If I put x equal to positive 1 into the derivative, I also get a positive gradient. So a positive, 0, positive gradient is a point of inflection. So then I know at x equal to 0, if I substitute y in, I get the point 0, 1. So x equal to 0 and y equal to 1, I've got a point of inflection. So it's going to come up, through, and continue up. All right, so I could find that x-intercept, and I'll do that because it's relatively straightforward. 2x cubed plus 1 is equal to 0. X cubed is equal to minus a half. X is equal to the cube root of minus a half, so it's a small negative number. So we write maybe minus a half to the power of a third. That point there is 0, 1. All right, so the key is we're going to use a lot of our graphing skills that we had when we did our quadratics and cubics earlier, factorising to find x-intercepts and things like that. But we now have a way of finding our turning points for each of those functions specifically. Okay, so a typical use of our derivative is to solve what we call maximum minimum problems. So as soon as we see any scenario where we need to find a maximum or a minimum value, by definition, that's where the gradient is 0. Okay, so it means it implies to us then, if we have to find a maximum or a minimum, we're probably going to need to find a derivative. Okay, so let's have a look. The canvas shelter is made up with a back, 2 square sides and a top. The area of canvas available is 24 meters squared. Find the dimensions of the shelter that will create the largest possible volume. So we've got the volume of like a box really, isn't it? So we know that volume is equal to length by width by height. Okay, and in this case, we've got x by y, which is equal to x times y, which is equal to x squared y. Now the problem we've got there is that we've got 2 variables still. So we need to find some relationship between x squared, or between x and y. So what information haven't we used yet? We haven't made use of the 24 meter squared area of canvas that's available. So I've got sort of 3 different shapes here, haven't I? 3 different side lengths. That one there, and we'll go with that one there. So I've got 4 sides. All right. So what are the dimensions of each of these sides? Well, the roof in yellow is x by y. So the area is equal to x times y plus my side lengths, which are x times x, 2 of them, plus the green backboard, which is again x times y. And all of those areas are equal to 24 metres squared of material. So that means, what have I got? I've got xy times 2 plus 2x squared is equal to 24. So that means y is equal to 24 minus 2x squared over 2x, which means y is equal to 12 minus x squared on x. So there's my relationship for y. So now this y value, which I'm going to highlight in green, I can now go to my rule for the volume and say it's x squared times y, which is equal to x squared times whatever y is, which is 12 minus x on x squared. So if I expand that now, that x, oops, that shouldn't be an x squared, it's an x. If I multiply the x squared through, that x cancels with that x squared, I get x times 12 minus x. Oops, I put the squared on the wrong spot. That looks better. So x times 12 minus x squared. So that's the rule for my volume. So volume is equal to 12x minus x cubed. So when does find the dimension of the shape with chrome? When does a maximum occur? Need the maximum volume, so I need to know where the derivative dv dx is equal to 0. So dv dx is equal to 12 minus 3x squared. Solve that equal to 0. 3x squared is equal to 12, x squared is equal to 4, x equals plus or minus 2. Now, obviously, our dimension of -2 makes no sense, so the side length must be 2 metres. So if the side length x is 2 metres, if I use my y relationship, y is equal to 12 minus 2 squared on 2, y is equal to 8 on 2, which is equal to 4 metres. So they're the dimensions of my box, or what are we making, a shelter, that gives me the largest possible volume. If I want to sketch this graph, if I come back down over here to the left, if I factorise that by taking x out, I get 12 minus x squared. So I get intercepts 0 and plus or minus the square root of 12, which obviously is 2 root 3. I won't worry about the -1 because because of the wonderful things, because we only need x to be greater than 0, don't we? So there's my intercepts. If I want to know where my turning points are, I need to solve my derivative equal to 0, and my turning points, excuse me, my turning points occur at plus or minus 2. So there's one turning point up here at 2. So my graph would look like, I don't need all that stuff, and then in here, up to 2, and then I'm going to stop there as well because I can't have a negative volume. So different points of view, but I think at x equal to 0, if the x value is 0, it means we don't have a shape. So we're not going to include 0, and I'm not going to include 2 root 3. The maximum volume occurs when x equals 2. We haven't found the largest volume yet. So my rule for the volume, if I put 2 into that, I get 2 times 12 minus 2 squared, which is 2 times 8, which is equal to 16 metres cubed. That's my largest volume. And then the final question says, find the values of x and y for which the volume is equal to 10. So let's come up here for part C. I want to solve the volume equal to 10. So what's my rule for the volume? So that means I've got to solve 12x minus x cubed is equal to 10. X cubed minus 12x plus 10 is equal to 0. And I'm going to solve that on my CAS. If I type into my CAS, solve x cubed minus 12x plus 10 equal to 0 for x, I'm going to get x is equal to 0.892 or 2.93. Okay, so there are two possible values for that. So I also know that y is equal to 12 minus x squared on x, and if I substitute those x values in, that'll give me y is equal to, so we'll get y equal to, what did we say, 12.55, is that pair, or 2.93, 1.16. So both of those sets of dimensions will give us a volume of 10 metres cubed.